All right, ladies and gentlemen, I know it's been long, but let's look at our very last example here. And this goes back to the study that they did on whether they feel the average normal body temperature is not 98.6 degrees Fahrenheit. So we've got our summary statistics over here. And if you were given a data set, you'd want to be able to graph that on your stat app to be able to find those summary statistics. And it does also look like, ladies and gentlemen, to be honest with you, our data does look fairly normal and bell-shaped. There is a little bit of an outlier out there, it looks like, but I mean, when we get to the requirements, it looks like those requirements are probably going to be met because he also did a simple sample. But I'm getting ahead of myself. So let's start off first of all again. We're going to test, is the average body temperature not 98.6 degrees based on the sample data? All right, so part A and B, we are talking about an average. So that is a sample, or excuse me, we are looking at a population mean. Our null and alternative hypothesis. Well, the null hypothesis is going to be that the average body temperature is 98.6 degrees Fahrenheit. And so the alternative, since they're saying, ladies and gentlemen, that it's not 98.6, we could test whether it's lower or higher than that. So the average, our alternative is going to be that it's not equal to 98.6 degrees Fahrenheit. And for part C, our alpha was given at a 0.01 level of significance. So alpha is going to be 0.01. So we look at our requirements to use a t-distribution. Well, ladies and gentlemen, I think we got a couple of them met. First of all, if you go back to the beginning, it doesn't say it right here, but if you go back to the beginning, it did say there that these individuals were randomly selected, so we do have a simple random sample, and our sample size is 130, which is greater than 30, which, ladies and gentlemen, will tell us that it will form a unimodal bell shape or symmetric distribution. And even if you look up here at the sample, you can see that you have, as we talked about before, a fairly symmetric, normal, unimodal distribution. So, the requirements are met, we're good to go. Now again, as always, I'm going to go ahead and graph this on the next slide. Sorry, the wrong way. So, if you take a look here, we do have a t-distribution. There's a center. Our degrees of freedom is 130 minus 1, which would be 129. And this is a two-tailed test. Why? Because if you take a look, it said not equal to in our alternative hypothesis. So that means our sample data could disprove the null on either side here. Now, when you do this, ladies and gentlemen, what we're doing is we're actually breaking alpha up, that 0.001, and splitting into two. So if you take 0.01 and divide it by 2, you get 0.005. Okay, about 5 thousandths in that tail. And you're taking alpha and splitting up here. You take 0.01 alpha divided by 2, you get 0.005. There you go. Okay. Now, again, is our data more extreme than either of those two tails? Well, we've got to then, ladies and gentlemen, calculate our test statistic. So again, this was E. And again, you don't have to draw a picture, ladies and gentlemen. I'm just doing it for the sake of maybe help you to visualize. Now, F is, we go ahead and calculate the test statistic. So, to do that, we take, again, our sample mean minus our hypothesized mean from the null hypothesis, that value from the null hypothesis, divided by the square root, divided by the sample standard deviation all over the square root of the sample size. So again, our sample data said that our mean was 98.25 degrees Fahrenheit minus hypothesized that we're assuming to be true unless our data shows us differently was 98.6 all over our sample standard deviation of 0.73 divided by the square root of our sample size, which is 130. Okay. Now, if you do that, you'll notice that this is a very small, I mean, this is way away from the mean here, okay, the mean of our sampling distribution. It ends up being negative 5.467. Now, that's telling us that, ladies and gentlemen, our sample data is somewhere way out over here. We need to find the p-value for it, but it's way out over here. We're about 5.5 standard errors away from the center of our sampling distribution. So we'll still find the p-value, but this is telling you that this is a very, very extreme set of data, okay? So let's go ahead and go to our stat app to see how far out we are. All right, what's our p-value? Oops. Minimize this. We're going to go to our stat app. We're going to go to normal distribution. Find a probability. Now remember, our degrees of freedom was 129. Don't use 130 there. This is a two-tailed test. Okay? Well, excuse me. I'm sorry. In this case, ladies and gentlemen, since our test statistic was a negative value, we're going to look in the lower tail for our probability value, okay, our p-value. So we're going to again, it's a two-tailed test, yes, but our probability value is going to come from the left tail because our test statistic was a negative value. So I'm going to type in here negative 5.467 right there. And you'll notice, ladies and gentlemen, that our p-value here is so small. It's not actually 0, but it's very, very close to 0. So while we write this for our p-value, again, we don't use percents as a probability value. It's not a percent. We just basically write as 0.00 plus, meaning it's very close to 0. As a matter of fact, I calculated on a different stat app, and the p-value was actually this. The p-value was 0.602. That means that only 2 out of every 10,000 samples will be more extreme than yours. This is a very extreme example, okay? And by the way, it's extreme not due to chance fluctuations in the sampling process. It's extreme because this is pretty convincing evidence that the null hypothesis is probably not true. Again, you don't have to write this because we're good enough with that, okay? So let's go back to our slide here. So for G, we found our p-value was equal to, it's pretty close to 0 according to what our stat says. So that means our p-value is less than alpha. Remember, alpha is 0.01. So what's left to do is write the conclusion, and that is we're going to reject the null hypothesis. Our sample data is so strong that it's not only going to reject it, it's really going to reject it. So I would even say when you write your conclusion, all we're basically going to say is there is sufficient evidence that the average human body temperature is not 98.6 degrees Fahrenheit. Matter of fact, you don't need to write this there, but I'd say there's extremely strong evidence that it's not. Matter of fact, it might even be, it's probably less than 98.6 degrees Fahrenheit, okay? So we might have to rethink what normal is for human, and this is not the first study to say this. So you people going to the medical field and nursing, you may want to look at this, because right now, the 98.6, according to a lot of sample evidence, ladies and gentlemen, may not be the average body temperature we all thought that it used to, that is what's commonly been said it is. So that's it. Ladies and gentlemen, I know this can be difficult, especially a lot of you have been telling me the other stuff, while you're watching the videos and so forth, that you understand confidence intervals, you understand the central limit theorems. If you don't understand this, ladies and gentlemen, please, please, please email me or call me, and I can go through problems with you. I can help you. It's probably not that you're having issues in a lot of places. It might be just one or two, like with a p-value, writing null and alternative hypothesis, so forth. We can get that squared up pretty quickly. So, Mr. Mueller, again, this is all for target 11.1, and so we've just done the student examples. Go to online. There should be some practice problems online and an answer key. So if you have any questions, please get a hold of me. And then we just have one more target, ladies and gentlemen. We're done. All right? So have a great day. Stay safe. Stay healthy.